By its nature, the workshop it should be interactive and engage everyone in the problem solving and the questions and answers. However, given the situation, I think it was best to do it online, and I'm hoping that you'll get the benefit out of what we have prepared today. Before I start, I'd like to thank our team at RIME, the BRP RIME, students and the research associates. This, although I had my class notes, but it had to be condensed to be made at least for today's presentation, and they were extremely helpful in doing so. So I want to thank all of them, and I want to acknowledge, their contribution. I'm hoping that I will be able to sustain this for the rest of the day. However, if I feel I'm getting any fatigue, I'll ask some of my colleagues to jump in and help out. So before we start, I think this is geared towards entry-level engineers. Some of you might be, advanced and you've done many designs yourself.
Professor, Hani, you are muted by someone.
Yeah, I don't know what happened. So my hands are off. Okay. I think some of you may have had the experience of doing design, and I think my intention here is to really give you the most updated, point in time of the ASH to LRFD. And I'll talk a little bit about the historical development so you would have a feeling of how did things change and why. I've been involved, I've been fortunate to be involved in the original calibration of the LRFD, which came out in 1994. And I also, not unfortunate, to be involved in 2014 in the second calibration, which was at the serviceability limit states. So I think this way you are really getting the inside story of what went on and what are the changes were based upon. Then we'll go into the trying to talk about what are the loads and how do we distribute loads into the different from the main system, which is the whole bridge with the girders and the diaphragms, to the per girder, because the design in ASH2 is done per element, per girder. So we will talk about how do we transfer all that complicated loading into a loading per girder. And then we move on to talk about design of the deck, and then we move on to talk about design of the girder. And I had more topics that I could cover. However, since we're going to be a resource for you, we will do it in the future. We'll have another day for steel bridges, so we might be able to cover a little bit more. So without any further ado, I want to thank also the BRB, at NJDOT, the BRB team, Ali, Eric, Anchor, for their suggestion. I think this is a good idea, even for us to recollect our thoughts and present you with what we call the state of the art. So as you can see, I just wanted to let me go back here one slide. So here I'm going to be looking at two screens on my monitor. So the picture that you see here is really from the Victory Bridge, and we were involved in putting sensors in the main navigation span, which is somewhere, on this side, which is, to your information, this is the longest segmental span in North America. It's, I think, 444 feet. And in that span, and this was built, and I think, finished in 2005. So this is now becoming a very, popular topic. I'm involved in one project on trying to develop the specification for load rating of segmental bridges, and bridges like a Victory Bridge is one of them. Okay, and here as I said earlier, this will be a 2-day workshop, and the first day we are doing it today. And it will be mainly for concrete bridges, mainly pre-stressed concrete bridges. And the second day, which will be sometime in January, and we will announce it depending on the schedule, will be on steel girder bridges. So the today's workshop, we will talk about mainly an overview, as I mentioned, the bridge design specification, and we'll move on as you. I hope that you have the handout so you can follow also and maybe take your own notes if needed. So it will be a full schedule today. We will take breaks, and I want to make it informal. So anytime someone has a question, please feel free to interrupt and raise your hand so that Checo can facilitate the question. If you want to put it in the chat, also I think my colleagues will keep an eye on the chat. If you don't want to, be heard, you could just send the chat, to them. So the first session, let me start by giving you just a very quick background on what is bridge engineering and how bridges evolved over time and what is the history behind bridges. In nature was a very important teacher, for the first the prehistoric times. When a tree falls down or over a river, then becomes a way for people to walk on it and cross from point A to point B. And so the prehistoric times, the material really dictated what would be the type of bridges. So you had only stone, you had wood. So there was nothing really more sophisticated other than the ingenuity of a human mind trying to come up with a way to cross from point A to point B. And then, after that came the Roman bridge builders. Really, the Romans contributed a lot to bridge engineering, and you could see that out of maybe military conquest, out of cultural, out of necessities to bring water, aqueducts. So there was a very important step in trying to get bridges. After the Roman Empire fell, and it is just there was nothing, and we call them the Dark Ages in bridges. But after that, in the Renaissance, as you can see in there, one of the earliest bridges in about this is in Pont d'Avignon. And they started doing the arch. I mean, if you could look at the Roman bridges, their arches were not more than 28 feet. They didn't have the span because they were very massive and they were very heavy. And then by experience, the engineers started, or the masons at that time, they started thinking about going larger and larger, to 50 feet and 60 feet long. And the arches, instead of being semicircular, they became elliptical and became they're wider. And then it evolved over time until our excuse me, until in the 18th century, where the cast iron started to come into play. So you can see how when materials start to evolve, the bridges and even buildings, they become, better and longer and more daring. And in the modern bridges, I mean, basically what we did get is the scientific way of doing it. We started analyzing bridges. We started, especially in the 1800s, 1900s, the basis for analyzing forces and stresses became very popular. The Pont de Chaussée in France, they started teaching. People started having, bridge societies, because that was a very important element, and the culture of any society. In some places, bridges were markets, were a center of where you had restaurants, you had, bustling places. It was a toll roads. To enter a city, you had to enter the bridge. It became a military post, and it had to be protected. So bridges, they became very important. And, I think, Woodrow Wilson said that you could tell people's culture from their bridges. And that's true. And the U.S., because it's a modern country. They started the longest span started in the United States, and mainly because of the necessities and including the first steel bridge, which was in Eads, which is still actually in place. If you visit St. Louis, you should see that. It's still in operation. I believe they only use railroad on it now, but it was the first cast iron place, and you can see they use the arch, which is the shape of what they had, the stone and the wood that they used. So they try to do it in the same manner with the trusses and then we came, which my favorite bridge, which is the Brooklyn Bridge, and it's a suspension bridge, but if you look closely, you can see that there are some cables stayed there. So it's a combination of suspension, and it's one of the story of the Brooklyn Bridge is one of the amazing stories, with George Roebling and his father and his wife, how that I don't know if ASE has a very nice short documentary on that, and it's really amazing. And then we go to the modern, longer, much thinner decks, and like the Verrazano. So the question is, where are we going with bridge engineering? And is the 21st century, going to be? Are we going to have a leap? Given that we have produced a lot of advanced material composites and a lot of enhanced engineering designs, more computer designs and better aerodynamic analysis. So we are trying to be daring. And I think for the last, maybe I would say 30 years, the Asian countries like South Korea, China, Japan, they had the advancement in bridge engineering, especially on long span bridges. And so with the presence of new material, it's yet to be seen. One of the concepts that I put those as an example. This is designed, the concept is by the late T.Y. Lin, and it's a combination of a hybrid cable stayed and a suspension bridge. If you see how it is, it's really, you're talking about 5,000 meters, spans, and that's unprecedented. It's just it's been designed, analyzed, and it seems to be, with the aerodynamic analysis, it works. And the Messina Bridge, for the last 30 years, they finally find up a design, but it was on and off because of the cost. And but now it's back on. In 2020, the Italian government announced that they will have $4 billion to do it, plus private investors, and it seems like it might happen. This one is about more than 3,000 meters span. One span, so that's really daring, and that's beyond what we have right now. I think right now we have like 5,000 feet at most. So I think with the presence of new materials, this will be a very daring century for bridges. However, in our everyday bridges, which is like the short to medium span, there are many issues that are coming up. And I think what the enhancement is going to be, are we going to design for 100-year service lives? I think durability and maintenance are becoming too important, more than safety and strength. So serviceability, design life, we can do it easily. The question is it possible to do a 100-year design life? Yeah, it is. We can design for a 100-year maximum moment or a 100-year maximum shear. However, the service life is different than design life, and we really need to pay attention to the service life. For example, the material we're going to be using, can they last more than 100 years? I think with the ultra high performance concrete and the carbon fiber composites, the fibers that we add, I think right now we have the material. I think it's just we need to have a little bit more daring. Like what happened, the shift from reinforced concrete to precast concrete on the turn of the last century. And this brings me to precast concrete, to the topic of the day. I think we have to give credit mainly to Eugene Fresinet, who was it happened that, he got into repairing one of the structure, the Pont de Verdure, And in that structure, he was trying to bring it back up. So he applied the cables and he tied them to the piers, and then added concrete in the middle to keep everything connected. And from there on, he started, patenting that. And this is in the left side is the first pre-stressing bed that he used to be able to use pre-stressing of concrete. And that's how around the 1912 or so, the pre-stressed concrete came to alive in this case. And so around 40 years later, this concept came to the U.S. The first time it came is in 1951, which city of Philadelphia, they brought in Gustav Magnell, who was a Belgian engineer, to design this bridge, and which is still in existence right now. And it's the Walnut Lane Bridge. It was built and designed specifically as pre-stressed concrete. And that was kind of the starting point in the 50s. And it picked up in the 70s more. And, and now we have, pre-stressed concrete is the main, you rarely see, other than short, culverts or anything like that, you rarely see reinforced concrete bridges. The reason is pre-stressed concrete, it showed its advancement, it showed its performance, especially at service. It's less cracking. And even if it has a hairline crack, the crack is usually closed, because it's usually in compression until you have live load on top of it, then it will open up and close again. Whereas in reinforced concrete, once it cracks, the crack might remain open, which will impact the corrosion of the rebar. So for today's concrete, I just put the Victory Bridge because this is one of the signature, I would say, bridges in New Jersey. Among all the bridges, I think this is an excellent design. Was done by FIG and constructed by George Arms Company. And I think this was, you have to give credit to the DOT at the time, the NJ DOT, for pushing this. And I think we were involved in trying to measure the creep and shrinkage in the middle. We placed some sensors in the middle span here. By the way, this was an I-35. This is the swing bridge that was there. And every time they would have navigation, they would swing the bridge. It will take about maybe at least half an hour to 40 minutes. Traffic would be stopped. So this bridge really solved the problem. And the swing bridge, I think, was removed. And I think it's in a museum somewhere. A piece of it is in a museum. These are the segments that they were done. And they were done in Bayshore, precast plant in Virginia, and they were shipped by the barges all the way to New Jersey, and then from the barge right to the construction and post-tensioning of the segments. So there are two types of pre-stressed concrete. There's a precast, pre-tension, and it can take different shapes. The pre-tension usually, we make them on the pre-stressing concrete plants, and it can be a composite with the decks, usually when we put them on the bridge. And there's also post-tensioning, which is, mainly an unbonded tendons. You could make a combination, especially in segmental, you would have to do a combination of bonded and unbonded. And, then you would either grout the unbonded tendons, and thus they would be more bonded and they behave integrally with the structure, or sometimes they leave them unbonded. However, in many cases now we are realizing that is for a steel tendon, that is an issue because there is water infiltration, sometimes even the grout. And about maybe 10 years ago, there was found that some of the grout had very high percentages of chloride in it. And then it was attacking the tendon, and a lot of the tendons were getting corroded because of that. So, the idea now we are moving towards, or at least our research, it's still in research stages, albeit it has been used in a couple of bridges, is to use non-metallic tendons, especially for unbonded. And the problem with unbonded tendons is they were very brittle compared to the steel tendons. but we proposing a combination of bonded steel and unbonded, FRP tendons. And by that combination, we are retaining the ductility and the cracking performance, the enhanced cracking performance that you would get. And I think with my colleague Adi Ubaida, we published a couple of papers on this topic. Now, the second one is the cast in place box girder. This is a very popular type of construction in California. And they are long, sometimes they are short, about 300 feet. And those, they have their advantages. However, I think for the speed of construction and, precast seems to be, the way to go. So this is a background about how the development of the bridge engineering and the invention of precast concrete. How did from the design side, where were we when these materials and when these developments have been happening? Did the design, specification kind of like follow up with what's going on and the advancement in the materials? Because they have to go hand in hand. To find new discoveries, we have to have ways of including those new discoveries into the design specs. And I think this is what LRFD brings into the table. So historically, it started with the allowable stress design. 100 years ago, probably more than 100 years ago, if you look at the codes, they were very, very simple, and it was based on the allowable stress design. We knew, steel and concrete at the time, and we knew at what tension the steel will fail, and what is the cracking and concrete, what is the strength of the concrete. And we basically put two allowable stresses. One is about 0.67 FY. FY at the time was about 36 KSI. You did the up to the point of cracking and compression, for the concrete, and even less than that. So those were the main thing that came about in 1931. And we've been designing bridges, and there has been a lot of debate from 1931 up to about in the early 70s, late 60s, when the method of ultimate design started to come into play, especially in the concrete and the reinforced concrete. And not only from the resistance side, but also there was a lot of debate since I think 1911 up to about 1943 about what the loads, because the trucking industry was changing. You're talking about small cars and horse and buggy to started having a box truck, small box trucks coming, used for freight, for moving freight. So there was a lot of debate about increasing the loads. And then it was agreed upon, because there were so many loads, H20, H15, and then the debate was stopped at HS20 was used, for this, and they put -44 to recognize that this was the load adopted in 1944, because there were so many other types of loads suggested. And so since 1944, the live load side of it was using the HS20, and it never really changed, even in 1971, when we changed to what we call from the allowable stress design to the load factor design. And that was really mainly driven by the concrete design, that we're now utilizing the concrete not only to the elastic limits, but we know that the concrete can take more than its elastic limit, but it will crack. And however, when it cracks, the steel is gonna do its job and take over. So we tried, so the idea was, ultimate design is you factor the loads, because we know that the steel can have more strength beyond its yielding, but however, the ductility there is gonna be a lot. So we don't wanna allow that to happen. So we factor the loads, we do all the designs of the ultimate, but we know most of the behavior is gonna be about 30% to about 50 to 60% of the ultimate loads. That's where most of the service loads are gonna be taking place. So because of that, when we factor the loads, that's all that has been done at that time. We just factored the loads so that we can do the design at the ultimate rather than at the elastic limit. So there was no calibration. We didn't know what was the safety associated with that. So we just took that there's a factor of safety. We didn't know exactly how that came about. So in 1987, I worked with my advisor, Professor Andy Novak, and we did the calibration of the Canadian code, the Ontario Highway Bridge Design Code. And that code over there was the first reliability-based code. The first edition came out in 1983. Second edition came out in 1989. Having the change in the North America and a country close to the United States, the Federal Highway and a lot of the bridge engineering community started thinking about this new approach from 1986. They started exploring, how about if we shift into this? And I think Mujeski and Masters, Dr. John Kulicki led that effort, and University of Michigan was involved in the calibration process, in the development of the load models, in the development of the safety load and resistance factors. And in 1994, so there was about more than 200 people meeting every 3 or 4 months. Sometimes they meet in different places, in DC or in Ann Arbor in Michigan, and they discussed the code. And then in 1993, it was the many versions of it came out. It was used by consultants, and the feedback that came back helped improve that specs. And M&M put it into vote, and the bridge community approved it in 1994. So this was the first time we got the AASHTO LRFD in 1994. And after that, many states were reluctant in trying to use it. I mean, because they didn't want to make the switch easily. One of them is because the AASHTO LFD, in some cases, the live load demand was lower, and now the HL93 loading has changed the way, especially with concrete, with pre-stressed concrete. So there was some reluctance in moving into it. However, New Jersey DOT in 2000, they decided, after we did a couple of workshops in 98 and 99, and I think the decision was to move to LRFD directly from allowable stress design. So the New Jersey DOT, they never really designed any bridges based on the LFD, believe it or not. They were always using allowable stress design because it was thought to be more more conservative, and this is what the decision was. And the Dorimos Avenue Bridge was the first bridge to be designed and constructed in 2003 based on the LRFD. And we had, with the help of DOT, we had a major effort in monitoring what the performance. So we had a lot of input about distribution factors, about deflection limits, about fatigue. So this was a very, interesting bridge. So, and now from that time on, the LRFD, every 4 years, it has been evolving and it has been approved. Major changes were done in the 4th edition, especially with the shear. When I worked on it, one of the objectives, my co-advisor, Professor Antoine Naaman, who's a pre-stressed concrete guy, was in charge of the pre-stressed or the concrete section of the specification. And one of the things he did, he came up with a concept of what we call structural concrete, meaning that you don't have to look at reinforced concrete alone or pre-stressed concrete alone. Structural concrete varies from, and he referred to it as the partial pre-stressing ratio, which is a value of 0 means it's reinforced concrete, and a value of 1 means it's a pre-stressed concrete. And the specs are still now, they're still unified in the AASHTO code. However, the shear part was handled by Professor Collins. It was the first time that we adopted at that time the modified compression field theory, which we will talk about a lot today, for shear. And the reason that was a big improvement over, the VS plus VC, approach that's still adopted by the ACI. And the reason, so it's the modified compression field theory is a little bit more complicated than the simplistic approach of VC and VS. That's empirical. This is rational. However, the ACI still sticks to the simplicity, and it's a little bit more conservative, so it's still at that. However, in the bridge engineering, we moved to the modified compression field theory. And at that time, between 98 up to about 2006, there were a lot of issues about the fact, especially with the load rating, that sometimes the answers came out not correct. And so Professor Collins took a sabbatical, and he went, and in 2006, he fixed it. He made it more adaptable towards a design. If you use the program, and it's available, it's called Response 2000. It's a very, very nice program. It's free. It's on the website on Toronto. You can download it. You can get the exact capacity. However, if you use the design procedure, that Professor Collins developed the first time, there was some kinks into it. And that's why, and you will see it in the code today, how we adjusted that. So what are the changes? What is so special about the LRFD? Well, the LRFD came out not only about the load and resistance factor or the calibration. There were a lot of new limit states introduced. For example, we always dealt with fatigue, but it was under steel limit state, but we made it its own separate because it's very critical. Extreme events like scour, like barge, impact, those were happening, although they were low probability events, but they were very high consequences. So these were made their own limit states in the code, and they were divided. The major part was development of the load. A lot of I was involved in that, and a lot of the states were split. Some states wanted to keep HS20. It says it doesn't represent actual truck traffic. That was the opposing point of view. But people said, we are familiar with it. We know it. Why would we want to do a composite truck? This is what the Ontario did. They had a truck. It's a made-up truck. It's not real, but it's an envelope for all the other trucks in the market at that time. This was done in Ontario. AASHTO did not want to go in that direction. They like familiarity with the HS20. However, the HS20 was light. It didn't really, cover. It didn't envelope, especially the grandfathered, or what we call the exclusion trucks. A lot of the states, in the early 70s, when the bridge formula came out and the legal load limits came out, some states, they've been grandfathered because they had been allowing a little bit higher. New Jersey is one of them, and the axle loads and the tandems and the gross vehicle weight. So at that time, some of the vehicles were heavier, and the HS20 wasn't enveloping that. That's why we used the legal trucks to be able to get that. So in a way, we needed something a little bit heavier, but to keep that familiarity, to keep that, same arrangements. And this is where I think Dr. Kulicki, with his, a combination of different loads, he came up with what was used to be used as a lane load. For those of you who don't know what the previous LFD, they used to design bridges by using what we call truck load or lane load. The reason is because on long span bridges, many trucks will be in traffic jam, and that represents a uniform distributed load. Whereas in shorter span bridges, one single truck will control in one lane, okay, or in two lanes. But so the truck load, which was the HS20, they would use that, find the moments per girder using their distribution factors, or you put the lane load, and the lane, and then you can get a different moment. It might be larger than the HS20 moment, so then you would say, okay, the lane load controls the design, and I'm going to use the moment from the lane load. And and usually the lane load controlled for spans above 120 feet. So if you were short to medium in the sense that 50 to about 100, 110 feet, it's always the HS20 truck that controls. So they're given those familiarity with both, and you're using them separate. Dr. Kulicki said, what about if we do both of them together? put the uniform load and then add the truck on it, and you put the truck where it will maximize your moment, right? And when we tried that combination, it looks like it envelopes everything, even the exclusion vehicles that you have seen. So the HL93 came about in trying to be a practical way to envelope most of the truckloads that you see, in the road these days. So, and then so now you have the load. How do you distribute it? Well, we know that the old distribution factors were not very good. They were conservative, and some, and when you go with the spacings a little bit larger, they became unconservative. And when the spacing was 6 feet, 4 feet, they were very conservative. And you didn't see bridges spaced more than 10 feet in those days. Right now, we talk about spacing of 12 feet and 14 feet. Well, why is that? Well, because of the high performance concrete, the higher capacity, the better distribution of the reinforcement. And when you do that, you are saving more girders, and that therefore you make your design a little bit more economical compared to the previous days. So before the NCHRP 1233, which is the project that did the development of the specs, there was a project 12-28. And the company named Roy Imson, an associate, and his team, Turuk Zakai, worked on that, and they developed distribution factors, but they're mainly based on finite element. So they took hundreds of bridges of different types, different width, different length, different number of girders, and they modeled them with finite element at that time. This is in the 88, finite element was becoming very popular, and they modeled them, and they did put the trucks different position. They got the distribution, and they did a regression analysis in the results, and they identified the parameters that make sense, so they affect the distribution, like this, the span length, the thickness of the, slab, the spacing between the girders, or all of these parameters they found to be influential. And then they did a regression analysis in all these parameters, and we came up with equations that are very complicated, in my opinion, at that time. And they were really rejected, by the users, because at that time people didn't use Excel as we do it today. They didn't use programs. And again, simplicity was always the key. So you're talking about if a factor, an equation that has to the power 0.1 or power point whatever, S and L and T, and some of it is iterative because you don't know what the girder stiffness ahead of time. So you really need to size the girder, then you go back and you iterate, with the girder moment of inertia, what was one of the parameters. So it was very complicated, and that's why LRFD, in my opinion, got a bad rap because of those complex factors. And that's why later on, there were many projects from NCHRP about developing simplified distribution factors. And using the Doremus Avenue, we did that. We did more simplified based, similar to what was in the old code. However, now that the people engineers are familiar with Excel, with the programming, it became a black box, and nobody really cares. I talked about the unified approach. And the sheet design and modified, we'll talk about that. That was totally new. Strut and tie model made it, to concrete, especially not everywhere, but it allowed the use for anchor zones, for pier caps. Some of that is being done. It's simplistic, but sometimes it gets more complicated. And the solution is not necessarily a unique solution. That's why it's not finding its way into the mainstream in a way. Okay, so there was a lot of improvement over ASD and LFD in the sense that now with the development of the load and resistance factors and the simulations that has been done, we made sure that all the designs have the same probability of failure. It means you have a uniform safety. If you build a wood bridge or a steel bridge or a precast concrete bridge, you should get the same safety level or probability of failure. And in the past, it was not the case. And it keeps that approach gives more room for people to be able to do include the new design equation. So the basic principle and I know I'm a little bit ahead of, behind time here, but that's okay. Let's continue, and we'll keep this going. The basic equation for, if you look at the LRFD, what does it mean? Well, what we're trying to say is that the loads are random variables. They change. There's a lot of uncertainty involved in quantifying what are the loads. If I ask you now, to stand by a bridge and tell me, the weight of the trucks and the number of trucks and the type of trucks, you would not be able to give me the same number or at least one number. It varies. The loads vary. The trucks vary. So there's a lot of variability in the weights and the distribution of the loads. So the live load is for sure not certain. And the way to accommodate for that, this is why the load factors are there. This is why, when you look at, let's say, 1.25 dead load plus 1.75 live load, you might ask the question, why do I have a live load factor for dead load lower than the live load? The live load is 1.75. It's because there's more uncertainty involved in trying to quantify the design live load. Therefore, you have to penalize that and make the loads even, higher, because you don't know if they will fall within that range. Whereas dead load, you can measure it. Even though you ask for a, let's say 12-inch WAP, you might get 13-inch WAP because the form might, so there is a little bit of increase in that, but not the variability. It's still more controlled, and that's why you have a lower factor. So the load factors are trying to accommodate the uncertainty in trying to estimate what are the loads. How do we get those? How do we, and then from the resistance side, you have the same thing. You ask for FY of steel of 60, maybe 98% of the times you get it above 60. But there will be times when you get it a little bit lower than 60. Although now there's a good control in the quality. However, the statistics of what we are getting shows that there are some samples that will be below the target values, right? So there is uncertainty there. Same thing with the concrete. We test a lot of cylinders in the lab. You are familiar with that in the field. You take samples, you test them. Not two samples are the same. The F prime of C will never be getting the same. So if you test enough samples, you will see that you will get a distribution. So each parameter that is part of the resistance equation is considered what we call a random variable. It's not random in the sense that it goes everywhere. It has a certain distribution that it follows its statistical data. So to be able to do the calibration for the first time, that was one of the difficult tasks because we didn't have statistical data on the material. We didn't have it. We had, anecdotal information, and some of it is biased. For example, we were trying to use the live load from the weigh stations on the side of the highway. But we were observing that there are no trucks above 80,000 pounds. So this is biased. We know that there are oval. Then we ended up, and I did that personally in my research, I used the first time the bridge weigh in motion system to get the weight of the truck without the trucks knowing that they're being weighed. And we observed when the weigh station was closed, when the weigh station was open, how much is the difference and how heavy trucks avoid the weigh station. So we ended up using the weigh in motion data that I collected in Michigan. The AASHTO refused to use it because Michigan had extremely heavy trucks, as you know. They allow 11 axle trucks, which is 162,000 pounds legal load, but it has 11 axles. And so it's very well distributed. But the gross vehicle weight is high, and they become very heavy, and they cannot use that as a standard for the nation. And we didn't have any WIM data at the time other than the one we had. So we ended up using the same truck population that we used when we calibrated the Ontario Bridge Design Code, which is the 10,000 trucks that were collected. Now, this equation here is exactly that. So you're trying to say that the loads, when I factor them and I apply the factor, this factor was introduced in AASHTO to represent three things. So this we have the I think called this new. I think new D is a Greek symbol. So one is for the ductility, one is for redundancy, and one is for importance. Those are factors. I don't have too much faith in those because those were just done to as a future placeholder, so that in the future we can get better factors to represent using ductile material versus a brittle material. However, they do the job right now, and they are they vary. They should be above 0.95, and then you would use that to reduce the loads with that, depending on the ductility that you have or redundancy that you have. When you factor the loads and you sum all the loads, dead load, live load, there's many load combinations, they have to be less than the reduced resistance. So you see the phi factor, this is very important. The phi factor is called the strength reduction factor. And that factor is a penalty because you are using approximate models to estimate the resistance. If it was a reinforced concrete section or precast concrete section, at ultimate, you are assuming the Whitney stress block to basically find out your compression force. In reality, that's a parabolic distribution, but you are using it as a modified rectangular shape to just help you calculate the area, and you're using 0.85 at prime of C as your stress, average stress. But the stress can be higher than that. But that's conservative. So because of that, you are penalized in a way to do that. However, you might see that some phi factors, like for steel and precast concrete, phi factor is 1, okay? And there's a reason for that, because the information that we got at that time from the industry, from the steel industry and the precast concrete industry, they have shown that they really reject material that's bad. And so that enhanced the performance, and therefore there is no need for a penalty. I don't agree with that at that time, and I still don't agree with it because the phi factor of 1 is calibrated anyway, so it doesn't really matter because the live load will reflect that. So the other thing is, how do you predict? I mean, when we talk about reliability-based design, you're collecting data on the loads for about, let's say, a 1 month or 1 year. But how do you predict what the loads are going to be in 75 years? So that was always the question. And, we dealt with that in a very, logical way. We used what we call a probability scale. So in other words, instead of using, you've probably seen those probability scale where the probability goes from 0 all the way to 99.999 at the top. However, this scale here is what we convert the probability into an inverse normal standard variate, meaning that for a probability of 50%, the inverse normal is about 0. So the mean value, if you look at 0 here, this is the mean, this is the 50% probability. If you go 1 up, that means it's 1 standard deviation up. So the probability here is 0.841 if you are doing in a probability scale. Why do we do it that way? Why? You probably have seen this a lot. Well, we plot the data that we collected, we take the trucks, we simulate them over different spans, and then we look at the upper tail, because this is what we're interested in. Those trucks, let's say they were 2 weeks. This is the data we collected from Ontario. And based on these 2 weeks trucks, we take the upper tail and we assume it is a linear normal distribution. Because in this plot, this is why they call it normal probability paper. And that means if a distribution is normal, then it will look approximately like a straight line. And more or less, this looks like a linear line. So if you extend that up to a different level, and if we know we have 10,000 trucks in 2 weeks, then based on the number of trucks in 1 month, 1 year, so we assume that it's the same truck flow every day, and we do that assumption, and then we extrapolate all the way down to about 75 years, and we pick that value as our expected maximum moment. So that is a procedure that has proven to be very, it's been done 30 years ago, but it has proven to be very, very valid. This has been done by Professor Lind and my advisor at the time, but we improved it, and this is the data that I worked on with Professor Novak and the Ontario data And we were able to solve that dilemma about the ultimate load. Now we have the loads. I cannot see if anybody is raising their hand. Chekok, you have to stop me because I don't know where the Teams thing went here. My screen is blocked with the PowerPoint. Are there any questions or?
No, I just asked you because of the time limit. It's 9:52.
Yeah, we will push the agenda. I mean, the example, I think we will be more speedy. I like to go over the behavior of this so we can get that.
Sure.
So for the limit state, I think the understanding of what is a limit state. So now, you understood how the background of the statistical information, how we dealt with the load, how we deal with the resistance. We assume that once we have the statistics, you are able to find the loads. If we draw the probability density function, and you are able to draw the resistance, the probability density function, and then comparing the two, if you take the resistance minus the load, that will be your reserve, your safety. And if you take that function, let's call it G, and you say R minus Q, and you plot it again, you will see that sometimes the loads are above the resistance, okay? And that is this shaded area here, okay? So if you take the integral of this function between minus infinity, okay, up to about 0, that is the area under the curve. And that's what we call the probability of failure, okay? So in a way, if you do that, you probably heard of beta. What is beta? Reliability index or safety index. This is nothing but the same graph, and this is R minus Q. So the more your mean value is away from the 0, the safer you are. Okay, so what does that mean? Well, that means you want to minimize the probability of failure, this one. So that means, you want to move this line as away as possible from the 0. To minimize this, you have to extend the distance. So this distance is called beta times standard deviation. So in other words, how many standard deviations away from the mean, away from the failure? So the limit state is this one. This is what we refer to. This is the limit. Below this one, you are failure. Above this one is safe. But how safe is safe? Okay. The safety is measured by beta. And when we say beta is 3.5, for example, that means your mean value, okay, is about 3.5 standard deviation away from the mean, from the 0, from the failure. Okay, so so that means what? That means you are using a probability of failure of 1 in about 5,000, or we call it 2 in 10,000, and sometimes people say it's about 1 in 10,000. Well, mathematically, this is the correct probability of failure, but it's a notional thing that we say it's 2 in 10,000, and people started saying it's 1 in 10,000. So this is the probability of failure in bridges. We assume it's about 1 in 5,000 bridges will have their loads a little bit above than the resistance. Now, this idea here is not about catastrophic failure. So even if sometimes the probability of failure, if the loads exceed the resistance, they usually don't exceed it by a lot. But that is failure. That's what defined by. It's not that the bridge will fall apart and collapse. That's not what it is meant to be. So if you look at how was the safety before in the old code, in the LFD code, versus the new safety now. So you can see that we took about 200 bridges from each state, donated about 3 bridges, and steel and precious concrete. And we analyzed all these bridges, and we found out their capacity and the loads, and we found out their beta. What is their beta? And you can see the variation with span length. That shouldn't be the case. And when we calibrated the bridge, after calibration, you can see you have more uniform, meaning that if a bridge is 50 feet or a bridge is 200 feet, it doesn't really matter. And you can see here for long spans, the average beta was getting higher because designers, by nature, they're more conservative. And the LRFD had more limit states in a way. And the limit state now, so I said strength. And for strength, you have about 5 of them. we're not going to cover all of them because they're not all relevant to our workshop today. Service limit state, there's about 4 of them, and like 1 and 3 apply to reinforced concrete and precast concrete. 2 applies to steel overloading. I believe 4 is also for long span, in a way, and same thing with fatigue. We had only 1 limit state, but in the recent after 2014, they introduced the infinite fatigue life and finite fatigue life. So if it's 75 years, then you call it finite fatigue life. But if you want to design a bridge to have infinite fatigue life that doesn't have a fatigue problem, then you would have to use the infinite fatigue life limit state. So that, and then you have extreme loads. So those are the limit states that you would have to address. And here, these are explaining each limit state. They're in the code. We are trying to give you the article. So you need to really to have a copy of the ASH2 LRFD to be able to follow this. So when you want to take this PowerPoint and look at the ASH2 code, we try to point out where it is in the code. And this is taken from the code, right? And so these are the service limit states. And this was calibrated before. The calibration was done based on ultimate limit state only. And later on, in 2014, it was concluded to do the service limit state were calibrated also. And you will find this in the table. This is a very important table. It's the load combination. So mainly we use dead load and live load. We always talk about that. But because that's what usually will control. But if you are in a place where snow or wind load or other limit states, you might have to check all of them. And for dead load, you have different types of dead load. DC, DW, wearing surface. They are sometimes dead load behave against you or with you. Meaning, if it's favorable, then you don't use the load factor of 0.9. You will see this some of the tables here. So this is for the DC component attachment. Like why would we have maximum and minimum? Well, the maximum is really when the dead load is behaving against your design, meaning that it's not helping you. Whereas the minimum is used when dead load is helping you. Like, well, how would the dead load be helping you? Well, if you have uplift wind, let's say, or if you have in a acute, in a very highly skew bridge, you might have this uplift of that, angle there. Some people do some tie downs. So dead load, in that case, the dead load, the weight of that deck at that point is helping you because it has to lift the dead load also. So you design a tie down, they tie it down. And I think in New York, I've seen a couple of bridges like that. So that is where, when you have uplift, for example, from wind or whatever it is, then the dead load, is resisting that uplift. Then you would use 0.9 with dead load because it's helping you. And so those are the others here. All the laws, they are, explained, in the commentary. And this is also, what we call for permanent loads due to superimposed deformation, especially for the DC component and attachment. And this one here, I'll explain a little bit. This came about as well adopted after our work on the serviceability calibration. Because when you are using precast concrete with the new losses, we used to use 0.8, but now with the new losses, because they're more exact, okay, then that means you are really right there on the money and you cannot really reduce the load. You have to take the full load, rather than using 0.8. The reason we use 0.8, this was a factor because HL93 was much heavier than before. You remember the HS20? And precast concrete design is not done at ultimate. It's done at service. So when you are using HL93, which is heavier than HS20, now you are penalizing the precast concrete industry because now you are telling them that the service load level is about 25% higher than the previous load. So that means they have to pick up a bigger section, which we know it used to work. So actually Dr. Kalicki came up with the idea that, okay, let's reduce that at service. So we use 0.8. And the reason that worked is because the losses were not very accurate at that time. But then when they changed the losses in 2005, they became very refined and more accurate, including the elastic gain. Then that meant that you are, estimating the pre-stressing force more accurately. So there's not much more reserve there. Then you are forced to use the 1.0. That was one of the recommendations. It was accepted and voted upon. How do you find from the loading? You have to find maximum moment. You're all familiar with influence lines, so you would have to do that. And what are the limit states? How do we use them? Well, for reinforced concrete, we put down what you have to do. You rarely, for both reinforced concrete and pre-stressing steel, you rarely have that, controlling your design. And, for the calibration, I just want to point out that for the calibration at service, we actually did calibration based on many, limit states. We did it on decompression, assuming that some states, they don't allow any tension, like New Jersey. They allow zero tension. So we did the calibration based on that. What would happen if you do your design on that basis? Some states, they say, well, we allow tension, we don't really care. And then we did the calibration based on that. And some states, very few, but nobody, likes that. But we did it anyway, just to see what happens. Is that what the Europeans call partially pre-stressed concrete, meaning you allow the crack, to happen. I mean, you design it in such a way that if it cracks, so what? The crack doesn't open and it doesn't propagate. Therefore, and they allow a maximum crack width. So we tried to do that. Although at the end, we stuck with this. I believe the calibration is based on that. We recommended some target betas. So we took all the bridges like we did with before, and we, found out what is the stresses, and we redesigned them. And we use this approach to pick up the reliability of beta. So here you can see beta is about 0.8 for decompression. It's not 3.5. This is the annual beta, right? For 1 year return. And if you allow the cracking, that then it goes up to about 3. This is what we proposed. But mainly the main work the work was based on a beta of 0.8. All right, so I think we are now, what time is it now? We are a little bit 15 minutes behind time, I believe. So let me just go through it. Are there any questions up to this point on the introduction? I know it took a little bit of time, but I think this will be going faster. Any questions?
Yeah, I don't see any question in the chat. Just one quick announcement. If you cannot download the file on the chat box, please text me. Send your email on the chat box. I'll send you by email. Thank you.
All right. So let me continue with this on the. So the ASH2 has a very.
I'm sorry, Professor.
Yes.
This is Najim. I joined about 9:20, so I had something to do. So
no problem.
I just want to. I'm sure Pranav made an introduction of the course, this workshop, but
we just started. We didn't.
Well,
I hope we started, really.
Huh?
It was already started.
Okay, so just for the. Did you make an introduction, Pranav?
No.
All right. Let me just quickly, okay?
Sure.
Professor, if you don't mind, I'm sorry, I had something to do. I couldn't join in until 9:20, but I was listening on the first session. I just want to briefly tell everybody that RIME, Rutgers RIME, offers this opportunity to DOT employees and engineers to learn the philosophy of this LRFD bridge design, with various examples in the design of concrete decks, pre-stressed concrete girders and steel girders based on ASH2 LRFD design specification and to conform with the NJDOT design manual. On that note, as everybody knows, Professor Hani Nassif is a reputable professor of structures at the Rutgers, and through BRP, We are very fortunate to have him to give us this workshop. So on that note, I'm sorry, Professor. I apologize. I was a little late, and I meant to join it at 9 o'clock, but I couldn't make it till 9:20. So therefore, we want to welcome you, and we appreciate giving this workshop.
Thank you, Ali. I appreciate this note from you and from everybody at DOT. I think we work as one team, and I'm really very happy to help out. I try to do everything we can. So we have a couple of examples at the end that will explain. But I wanted to go through the background of the code because I think that will be retained. And that's what I do in my class. I have, by the way, and I don't want to advertise my classes, but we have two bridge design classes. One is Bridge Design 1 and then Bridge Design 2. And in the Bridge Design 1, I go over girder bridges mainly, steel and precast concrete. And we have a project that we do it from almost A to Z. And in the Bridge Design 2, we do advanced topics, mainly analysis, modeling, even testing. Sometimes we put data, how to process the data. So, and then we have I have precast concrete design, and then I have also reliability course at IT. So those are the 4 courses that describe really what we have been doing. And I invite all of you to join our graduate program and do a master's degree in structural engineering. And you'll be very happy to receive all, especially in bridges. We are very heavy on that. Anyway, so let me continue. I sorry that I did not allow or I forgot they needed to do for Parnav. I think Chekhov made the introduction, but thank you for this introduction, Ali, and I welcome everyone again. So this LRFD has a definition of all the loads, as I said earlier. Okay. Now we described, for example, you might see like why do you have like more than one kind or 3 kinds of dead load? Well, because the statistics of the variances in dead load are different. In what way? Well, if you take asphalt, for example, you ask them for 5-inch thickness, it might go up, not now, maybe now with the laser technology, they do it very precise. But in many cases, if you do coring of asphalt, you'll find in some places it's about 3 inches and some places 9 inches. And that variability has to be reflected in the code. That's why we use 1.5. And if you do cast in place, it's 1.35. And if you do like a girder, it's 1.25. So the value of the dead load factor represents the variability in different kinds of dead load. Before, they were all lump sum in one dead load type, but they're different. And that's why we have different load factor for DC and DW. Okay. For live load, as I said earlier, this is the familiar, I'm sure you are all familiar with the HS20 truck, okay? And, and it didn't, and they had a variable, especially for fatigue purposes to maximize the live load. And they had the tandem, okay, which was the 25 kip, and 4 feet, which usually it used to represent a military load, like a tank or something like that, and then you have the lane load. In the new HL93, this were combined. So for very short spans, like 20 to about 40 feet, this will usually control, and for spans above 40 feet or 50 feet, this will control. So now you have this plus this, or this plus this. So the lane load is jointly with the truck load or the tandem. Okay. In I have to say something because I used a lot of WIM data over my career. In the last 25 years, I discovered that the tandem, and we did also make recommendation, but there was no response to increase the tandem because the axle loads are heavy. Okay, in the WIM data, if you observe them, the axle loads are heavy. And this is the permit truck. I think I worked on it, I think, with at that time Jose Lopez and the late Jerry Semner. They did this work, and we looked at what Pennsylvania has done at the time. I think they had, and then this was the New Jersey permit vehicle, which you have to use for strength 2 limit state, and we'll see in the example how is that being done. Okay. And for the live load, so you really need to look at, you don't look at the traffic lane. We look at design lane, meaning that it doesn't matter if you have only 2 traffic lane and 2 shoulder. As long as you can fit a truck with a certain arrangement, 6 foot and then 4 feet and then another 6 foot, another truck and so forth, and the uniform load will be everywhere, then you have to maximize your total moment based on the number of design lane. How do you calculate the design lane? You divide the total width between the gutter, between the edge of the parapet here, we divide it by 12. So the design lane is assumed to be 12 feet wide. So if you have a 48-foot, curb to curb distance, that's what you would use. You divide it by 12, that's 4 lane. So you would assume you have 4 design lanes that you would have to use. And it doesn't matter if the traffic is an opposite direction, they are all considered part of it. For negative moment, one of the things that we tried to do at that time is that the single truck will not control, so you would have to have 2 trucks. And if you draw the influence line for the moment, I don't know if I can, I think I can write with this one here. Let me use the pen, sorry. So if you do the influence line for a moment, for continuous span moment, it will be, and this is the middle support here, it will be something like this, let's say. And then that, this should be upward, be positive. So that this truck has to be placed somewhere to maximize the moment. And this second truck has to be placed here to maximize the moment. And we found out that usually it happens when this distance is about 50 feet, okay? So if you take 2 trucks with the headway distance 50 feet, that's what this is coming from. The headway, maybe now in traffic jam, it will be shorter than that, right? But then you will be away from where the maximum moment is. So 50 feet, usually if you have a spans, each is 100 feet, you will be probably 50 feet is reasonable to do that. And then that will give you the maximum moment, and the uniform load is applied on all the span at the same time. And this is the, so now what happens, this is in 1 lane. What happens if you are loading multiple lanes? Well, this is what we call multiple presence factor. So that depends. In the past, the LFD, they had, for 1 lane, they had it 1. For 2 lane, they had it 1. But for 3 lanes, they had it 0.85. And then for more, they had it, I think, 0.85. In this specs, when we did the simulation, we found out that what controls the moment most of the time is 2 trucks side by side. This will always give you a larger moment than a single lane. Even though the fact that when you have 2 trucks side by side, the probabilities are less, and the correlation between the heavy weights are going to be less. Okay, but we made assumptions at that point. Now we have more data to confirm that. But based on that, we said, well, this here will be the base case. So that will be your 1. And then if you go to 3 lanes, the probability of having 3 trucks in 3 lanes simultaneously with having the same weight is very, very low. So you have to reduce, so since that's the case, then we reduced it to 0.8. And the same thing, if you have more lanes than 3 lanes are loaded, which is a very, very low probability, even in traffic jams, you will never see 4 trucks or 5 trucks if you have 5 lanes. They're all stacked at the same point of maximum moment with the same truck. So that is where this 0.65 coming from. Sorry. So what about this? People will say, okay, so why? Well, if you look at it, in a single, you want to keep this 2-lane case close to the single lane case. So the single truck might be much, much heavier than 2 trucks side by side. The weight of 1 truck in side by side is always less than the maximum truck in 1 lane. Because of that, you have to penalize that, and you have to add 20% more to make them comparable to each other. And that's where the multiple presence factor came from. Okay. And the impact factor, if you remember, there was an equation. Some of you might remember the senior, but the impact factor, the impact factor here, I was equal to 125, okay. 50, plus L. It was 50 divided by 25 plus L. And such that it is always less than 0.3. Okay. That was the old code. So the impact factor, you said, why is that? Well, if you look at this, and this is a real curve. This was, we done that during the in the calibration. The impact factor is representing when the truck is going over the highway, it's going at a speed with the road roughness, there will be a lot of vibration, and that vibration will do some dynamic amplification. And the dashed line is the static line. If you move the truck at a crawling speed, then you will have this static line. So the difference is that the bridge is feeling this point, is being stressed up to this point. So you gotta account for that. The way we do it is we take whatever is static from the design, you put an HS20 truck, you find the maximum moment, and then you multiply it by a certain factor to basically accommodate for this amplification. Now, in the past, it was this equation. And if the bridge was 100 feet, you'll get something about 0.25, 0.27. So your value I was always going to be between 0.25 to 0.3. Okay, that was the range. However, in many cases, what we observed is that the impact factor is dependent on the weight of the truck, because I did measurements and for heavy trucks and for the light trucks. And some codes were written such that it's very high amplification, but those were very light trucks, not very heavy. And we designed for the heavy trucks. Or some trucks, they had some suspension different, air suspensions versus multi-leaf spring suspension, or the roughness of the road. So there were many, many factors, and this equation didn't really give any justice to that performance, okay? Because there's interaction. There's a dynamic interaction between the truck and the bridge as they go, and the roughness and the width of the bridge. Some codes had it as based on the natural frequency of the bridge, because it depends. The frequency of the truck is about 2 to 5 hertz. If you have the bridge between those frequencies, then that will cause some resonance, and that will help. It will make the bridge vibrate a lot. So those we opted, recommended to Ashto that take it out, and then just put 0.83%. Okay, because we found out for heavy trucks is about 10-15% for heavy truck. And we recommended this constant value, and then Ashto approved it. And this value here was not recommended. It was as is before. They were using it. We kept it because we don't have any information where they come from. Okay. But obviously for fatigue, because you're talking about the average stress, then this might make sense. But we have a student working on that now. And for other deck joints and all of that, we kept it the way 75% because that was perceived. There are other forces you have to look at, but those are the main thing that you wanna take away today. From the lecture, I'd like you to focus on dead load and live load. The other factors there, the centrifugal force, the collision force, etc. Those are things, and there's a braking force. When the truck brakes, the friction, it might, allow the bearings to be affected. There's wind load. All of that is explained in the code, but we're talking about basic design, so I'm not gonna go through that part of it, okay? And now I want to talk about how do we go from this global behavior of the bridge into a girder per girder? Because as I said, you're doing the design per girder. So you have the loads, you apply the load here, but the load is distributed to all the girders in a way, one way or another. and through the slab. So the slab is the transverse, it helps the transverse, and sometimes we put more diaphragm, and the diaphragm, they don't really do much. They just allow you for stability of the girder, especially during construction. They don't allow you more than that. But so how is the distribution? Well, ASHTO came up with a very, as I mentioned earlier, we tried to look at different bridges, and then these are the equations I was talking about, the one that Impson and Associates group did, and it was an NCHRP project, and we were told that you have to use them because this is a project that was done, and Federal Highway, they want to use this because they're very accurate. And they're true, they're very accurate because they are regression analysis of finite element results. And they, try different bridges. So they put you will see tables in the code. So if you are using like a precast concrete double T beams, you would use that section. Then the bridge type is I. So you would go for this bridge and for one lane, or whatever that applies. So they give you like for A and B, and you have the letters here like I and A. You would use this equation for one lane and this equation for 2-lane loaded. Okay, so you would use those. You can see K here is a factor that depends on the girder stiffness, on the distance between the center of the slab and the center of the girder. But in many cases, you know the girder, but sometimes you start to design and you have to change it. Okay, in many cases you don't know, you have to design the slab. You need to do that. So this is why they're iterative, and the same thing for shear. Now another way, these equations are very good for regular bridges, but when you have an overhang, a long overhang, or some cases where you still do basic, what we call the lever rule is still, this was carry over from the previous code. What does the lever rule say? Well, it says that, especially for the exterior girder, okay, here, it says that assume that there's a hinge here, and you have a simply supported beam with a propped cantilever here. You apply a load, you find the reaction, okay, these are the wheel load, so you find the resultant of the wheel loads, and the wheel load, the maximum you can put it to the curb, to the edge of the curb, is 2 feet. Assuming that the wheel, it cannot go beyond that point. And then you find the reaction, and that, percentage, 9/12, is the percentage of how much of this load is going to be distributed to the exterior girder. Okay, so it's very simple rule, and sometimes in many cases it's easier than using that equations if you need to do that. And it gives you here the cases where you could do that, okay, for one design lane. And in some cases, especially if you have narrow bridges, sometimes when you put the truck on one side, there's a fear that it might twist it and it might have a different torsional mode. So you could look at this distribution in this girder by using this equation, okay? And I give an example here. However, this equation does not have, you have to multiply it by 1.2 because it's a single lane truck, okay? It's a single lane, and these equations here, these equations, they already have the multiple presence factor included in them, okay? So you don't really, if you are using the code distribution factors, you don't have to multiply, even if it's a single lane or a double lane, you don't have to apply the multiple presence factor. But if you are using this method here, the one lane loaded, you have to multiply it by the 1.2, okay, which is shown here, okay. Okay, so now we are, I think this is catching up.
We have a 10-minute break.
10 minutes break? Okay, yeah. Let's do that. Let's come back at 10, now it's 10:30, let's come back 10:35 maybe?
Sure, it's 10:26, we'll come back at 10:35.
10:45?
No, 10:35. Right now it's 10:26.
Okay.
So
All right, 10:35 then. Are there any questions in the meantime? If anybody wants to take a break, but I'm willing to take any questions so far.
No, there's no question in the chat box. So if you have any question, please unmute yourself and ask question.
Okay, so we'll take a break for 10 minutes now, right? 10:35. Thank you.